Okay. So I'm going to present some of the recent works that I've done with my collaborators, specifically with Mathieu Viard and Mario Gage, which is also here and is going to present the next talk. And we're going to talk about the loss landscape in deep networks and the generalization performance in these networks. So first, before introducing the questions that I'm interested in, let me give just a brief overview and the setup. So I'm going to talk about supervised deep learning. This means that I'm interested in learning some rule from data. We will have some train set, some collection of data from which we want to extract some information. Specifically, the simplest setting is that of binary classification, for instance, of pictures. So you should think that you have a collection of pictures of cats and dogs, for instance, and you want to devise some function that is able to take a positive value on cats and negative value on dogs in such a way that you can perform this classification. Now, then after you find this function, you want to evaluate its performance by testing it over some data that you didn't use for training. Now, this is maybe the prototype of supervised deep learning. It is well known to work amazingly well, especially on images indeed, but still there are plenty of open questions and it's not really clear why it works so well. So in this talk I'm going to address some of these questions. And in general, if you want to have some questions in mind, you want to understand how many data are needed to learn a specific task and how big a network should be in order to achieve a good performance. So, of course, you can choose an architecture in many different ways. I'm going to talk only about the simplest architecture. So the function that you want to find is parameterized by a set of parameters. And this parameterization takes the form of a network, of a feed-forward network. So the input of this function corresponds to the first nodes in this network. And then you have a succession of intermediary layers. In these simple architectures, I'm just considering a fixed number of layers L, and each layer has the same number of neurons H. What each neuron is doing is just a weighted sum of the incoming signals of the previous layer. And then you compute a nonlinear function at each neuron and you pass on the signal. You can view this process also as some propagation of signals through a network from the input to the output. For what regards the dataset, we used different datasets. For most of the results that I'm going to present, I'm only using MNIST. You already seen this dataset. It's just a collection of digits and written digits. Since we want to do binary classification, because it's the simplest possible task, I grouped the digits into two classes with even numbers and odd numbers. And the expected label will be +1 for even numbers and -1 for odd numbers. Now, I denote by P the size of this dataset. Now, and x1 to xp is just the vectors representing all the images. Now, in principle, MNIST is a dataset with a fixed number of images, 70,000. What I'm going to do is to extract a random subset of size P so that I can vary the size of this dataset while keeping it statistically equivalent in some sense. And of course, I'm also extracting another subset to evaluate the generalization error. So here is the outline of my talk. There are two questions that I want to answer. In general, I want to vary the size of the network. So we keep the number of layers fixed, and we vary the width h of each layer. By doing this, we actually are playing with the number of parameters in the whole model. So the first question that we will address is, can we actually fit all the training data? Can we manage to learn at least the training dataset? And the second question will be actually on the test part. That is, what about the generalization? What happens to the test error if you vary the number of parameters? This, of course, is part of a long-term goal that is, given a dataset, given a task, what is the best architecture that you should use? And given the architecture, how do you choose its size, its scale? So let's start with the first point. First of all, what does it mean to learn? Learning means finding this representation, the parameterization for which you achieve a function. You find a function that takes the correct sign given the input. So if you have an input xi that corresponds to an even number, you want the function to be positive. And if you have an input that corresponds to an odd number, you want the function to be negative. I repeat, in this setting, for binary classification, the labels are just plus or minus 1. And in order to find these parameters, what you do in statistics, in inference, in every field is just to minimize the specific loss function. And of course, you have the freedom to choose the loss function that you want. In general, different loss functions can have different performances. And for classification in machine learning, the loss function that is the most widely used is called the cross entropy. The cross entropy, let me tell you. So first, the loss is, you write it as a sum of individual contributions corresponding to each training data. And for binary classification, what you want to do is to fix the sign of f to be equal to the label. So you can see that here this individual loss, this individual term, is just some kind of potential, or physical potential, that pushes the argument to be positive. The cross entropy for binary classification takes the form of a decaying exponential. It is this blue curve. You see, in physical terms, if you think that this is just a potential, it wants to push the argument to the right. Now, instead of using this cross entropy, we use the different function. We use what is called the quadratic hinge loss, which is the orange curve. It is more or less the same. You see that they are qualitatively very similar. This quadratic hinge is just a quadratic function up to some margin 1, and beyond this value, you fix it to 0. You put some hard cutoff. Let me tell you that we tried to take one of the state-of-the-art models on binary classification. We substituted the cross entropy with this quadratic hinge, and we found the same exact performance. So by changing this loss function, at least in this case, we're not degrading the system. We're studying a system that is very similar conceptually. Moreover, one of the advantages of this choice is that you see, suppose that you manage to fit all your points beyond this margin 1. It means that your loss is identically 0. If your loss is identically 0, it means that your algorithm knows when to stop, and it can do this in a finite time. Furthermore, there will be also another reason for using this function that will be clear in a couple of slides.
So you fix the margin?
Yes, 1, yes.
So what happens if you take it close?
So you can change this margin. The point is that the value of this margin, what does it mean? In practice, this function is something like the square of 1 minus y times f, times a theta function. You want this to be positive. If you change the margin, it's equivalent to rescaling the parameters. So if you change this parameter, this margin that we call typically epsilon, in order to have the proper initialization, you also have to change the variance of your parameters at initialization. If you don't do this, you are suboptimal. Yeah.
So this quadratic hinge is just x minus 1 square or something?
Yes, yes,
0.
exactly, yes.
But you could also...
You can choose the slope in principle, yes. Yeah. But changing the slope means changing the scale of the loss. That is just changing the learning rate. Yeah. And okay, so this is the loss function that we are using. So how do we learn? We want to minimize this loss function, and to do this, you've seen that there are plenty of different algorithms. We choose the simplest possible one, that is a full batch vanilla gradient descent. We can do this because MNIST is a relatively simple dataset, it's pretty small. And what is important is that we start with random initial conditions in the parameters. I will maybe touch this point later, but this is very important. You have to initialize your parameters with the proper variance. If you don't do this, or if you use the wrong variance, signals do not propagate through the network and you cannot train them, at least not efficiently. So here, what I'm telling you is that we have to minimize a function that is very high dimensional, because the number of parameters in this network is typically millions, if not even billions. It is not convex with respect to the parameters. I mean, the loss function is convex with respect to the output function, but not with respect to the parameters. And it's random either because you have at least the random initial conditions, or also because you can think that the data set that you're using, the real data, is just some random instance of real world data. If you say to a physicist that you want to minimize some random high dimensional not convex function, what he thinks of is spin glasses. And in spin glasses, as you've learned by now, you expect to have local minima at all possible scales in energy, and if you try any simple local algorithm, you get stuck to some relatively high energy local minima. It turns out that in practice, if you try to minimize these functions, if you try to train these networks, you typically always succeed. You find relatively low energy minima, you find relatively good performance in terms of generalization.
What are you saying? If you try to minimize the function of spin glasses?
No, of networks, of deep networks, sorry. If you try to train one of these networks on a real data on MNIST, you can do this. It's a very simple problem.
But you have a minimum.
Well, this is a different question, but already the fact that you find something that performs well, that has good generalization, is already a hint that you are in a good minimum. Whether it is high energy or not, still it leaves some open questions, because if you have some high energy minimum that performs well, it is still puzzling. But we're going to see that in our specific case, you actually go to the bottom of the landscape, at least in some regimes. And in general, you do not get stuck in bad local minima. They all seem to work fine. And this is true for every instance. If you redo a simulation, you always find another minimum that is different in general, but it has the same generalization performances. So one of the questions is to understand what is the geometry of this landscape. And also another remarkable result is that if you look at the landscape after you perform your minimization, in the end, it seems that you have a lot of flat directions. We're going to comment this in a couple of slides. But another interesting result is that it has been shown by Saguna. If you train two different initializations of the same network, you find two different minima, but typically you can find a almost flat path that joins the two solutions. And this suggests that the space of solutions is almost connected and very large in some sense. Now, here I'm going to present the results that we found thanks to an analogy with physical transition with a physical system. And let me tell you just in 2 minutes what this is about. Consider a system that is called, we want to study random packings of particles, of granular matter. Imagine that you have particles interacting with some pairwise potential, you put them in a box, you put them at random at some initial conditions, and then you minimize this energy, the sum of these pairwise interactions, in order to find the configuration that accommodate the particles in the best way. This is a very realistic problem. For instance, if you think of glass, it's something like this. You can have very different properties if you have a dense phase, which is more or less the glass in the windows where nothing can move, or if it is in the liquid phase, which is just a liquid where everything can move freely. Now, physicists have realized that this problem becomes much simpler to study if instead of considering any pairwise interaction, you just consider a finite range interaction. So you cut off the interaction to finite range. In the end, this is tantamount to considering contact forces between particles. If you do this, you can see that there is a sharp phase transition in the physical sense between these two phases. So you have critical exponents in between when you're at this so-called jamming transition. And you see the analogy. Here we're doing something very similar. We start from some random initial conditions. We want to minimize some energy. And according to what is the size of our dataset, we will find either zero energy or a positive energy, positive error, a positive loss. So before moving on to the results, let me also open a parenthesis. There is Franz and Parisi have already shown that there is an exact analogy between packings of spheres and shallow networks, that is perceptrons, for instance. Now, it turns out that the transition describing that appears in these systems is sensitive to the shape of these objects, of these particles. And in particular, if you use, for instance, ellipsoids instead of spheres, you have different properties, different critical exponents, and a slightly different criticality. What I'm going to tell you is that deep networks with more than one hidden layer, they're actually similar to these two packings of ellipses. At least they have a jamming transition that will share some properties. So what are these results? Well, first of all, let me show a theoretical phase diagram. Here I'm plotting the dataset size. So this is the size of the random subset that I am starting for, say, MNIST. And this is the size of the network. There are actually two phases. If your network is sufficiently overparameterized, then you can learn all your training set. You can achieve zero loss. If it is underparameterized, if it is not big enough, then you cannot learn everything. You have a finite positive loss, and this is this red underparameterized phase. In between, there is a critical line. There is this jamming line that I'm denoting as N star. And here, there are many properties that resemble those of jamming. For instance, if you move across this line, you have here zero loss and then a continuously increasing loss. You can consider something like that. You can count the number of terms that have a margin that is smaller than zero, and that jumps discontinuously at this line. Here you have critical exponents in power laws that I'm not going to show because we don't really have a lot of time. But there are really a lot of properties that scream critical phase transition. Now, we can derive with some arguments an upper bound for this transition. This upper bound says just that this line is below some constant times P, the size of the dataset.
So the upper bound means what? It's a refutation below, or it's above it's
above is for sure you can fit. Yeah.
But below you don't.
Exactly, yes. Above this line, for sure, your loss is zero, the loss at the end. Now, for this, we had to make a couple of assumptions. First of all, we have to assume that signals propagate through the network, otherwise you have to talk about effective degrees of freedom that can be effectively smaller, just like in the case of jamming. And for simple cases, for instance, for ReLU networks, we can actually compute this constant, which is 1/2. In general, this depends on some properties of Hessians, and we don't know anything, but we postulate that it is over the 1.
Could you repeat what happens above the line?
Yes, above the lane, we can guarantee that you achieve zero loss.
We achieve?
Zero loss, zero error.
Is it a training loss or
It is the training. Yeah, here I'm talking only about training loss.
you are talking about training loss?
Yes, yeah. Here it means that here you can fit your training dataset. It says nothing about the generalization. I'm going to talk about this later.
So in my language, you're saying that this is a class 1 problem, a simple problem.
Well, it is, yes, yes.
You don't need N to be like P log P or
No,
anything,
indeed.
just P.
Yes,
Constant,
exactly.
and you
Yes.
know the constant.
Yes, exactly.
So the gradient in the mediocrity region must be non-zero.
Yes, exactly. Well, regarding the dynamics, we actually don't know much. We can only say that here you can reach the bottom of the landscape. But this doesn't say anything about the existence of metastable states, of local minima.
So when you say you can reach, is it a dynamical?
No, this is the condition for being in a stable minima. We can derive this bound. So I mean, the parity of the condition.
It's a
yes.
statistical threshold. Not
Yes,
algorithm.
exactly. Yes. Yes. No. This has nothing to do with dynamics. Yes. Yes. Sorry, this is something that I had to say.
Architecture is fixed.
What?
Architecture.
Yeah, here the architecture is fixed. When I play with N, when I change N, I'm just changing the width of the intermediary of the hidden layers. But the architecture is fixed and the depth is fixed. If you change the architecture, probably this figure is going to change. The jamming line is going to change.
A single hidden layer.
This is for any. We tried for 2 hidden layers up to 10 hidden layers, but we keep that fixed. When you want to design this plot, you keep the depth fixed. If you change the depth, you have different jamming lines.
Then what is jamming line is?
So this jamming line is the line that I'm going to show. Let me just go to the next slide. So this is the numerical data. Okay. Here, I'm taking different values, different sizes of the dataset. For each dataset, you can train networks of varying size. And here I'm just plotting the loss, the training loss at the end of training. Blue points means that they achieved zero loss. All the other points, so this red and pale blue, they achieve a finite positive loss. Okay. So this boundary between the points is this jamming transition. Above, you can find zero loss, zero training loss, and it means that you can fit all the points. Below, no. Below, you don't have enough complexity in your model to actually learn all these points.
So this jamming line, you really got it from a model of jamming, or?
No, so the bound or?
No, they want.
No, that was just a sketch. Yeah, that was
just
yes.
artistic rendering.
Yes. Also, notice that this line will depend on the structure of your dataset, because you see, for random data, this line is a straight line. Because of course, you double your dataset, you need more parameters to learn. There is no structure, no information. If you have some information, just like in MNIST, this curve has to be convex. At least we didn't prove this, but it makes sense. At some point, if you add enough information, you don't need more neurons in a linear way to understand the same information. So yeah, it is specific to a single dataset and a single architecture, probably. Okay, so what I was telling you, the interesting consequence is that here, I know nothing about the dynamics, but here, for this loss, if you find zero loss, it means that you are really at the bottom of the landscape, because this is the global minimum, and your dynamics has to be simple, because even if there are local minima at high level, you don't find them, or at least you don't get stuck in them.
One thing that I don't understand, so it all makes a lot of sense to me from an information theoretical point of view. If you think about channel recording, so it is really spheres. Each one of the codebars is a sphere in a high-dimensional space, and you're trying to fit them also. But aren't they being distorted by the nonlinearity in the multilayer network?
There is also another difference that, so for spheres, there is the exact analogy with perceptrons. Here, the analogy is not exact because if you cannot have this analogy with particles because the network has all the patterns are interacting, they are shared. I don't know if you see what I'm saying, but if you write down the loss for the two systems, it seems the same because it's some sum over constraints, but the constraints for spheres are ellipsoids, they're pairwise independent, it depends only on pairs. Here, it is the output of a function, and all outputs share the same parameters. So it's much more involved. This is all the results that we have is they just follow some necessary conditions on the stability of the Hamiltonian or of the Hessian, sorry. But we know nothing about the dynamics and everything and anything else.
But you say you know nothing. You've tried. Oh, this is obtained through.
This is numerical. Yeah, indeed. I mean, the dynamics does not contradict this is for sure. But you know, in principle, this result doesn't imply that you can actually find the minimum. Okay, we can also have other results regarding the geometry of this landscape. In order to study the landscape, what you can do is to study the quadratic approximation of the landscape around the point that you find with your algorithm. So when I say quadratic approximation, it means that you find the best quadratic that approximates your landscape. You see that this is an example in two dimensions. You can have if you have a good minimum, as you would expect, you have all positive directions, positive curvatures around you. But in some degenerate case, you can also have some flat directions and some other positive directions. And in general, for saddle points, you can also have some negative directions and positive directions. All this information is contained in the Hessian matrix, that is the matrix of second derivatives of the loss with respect to the parameters. And if you look at the spectrum of the Hessian, that is the distribution of its eigenvalues, you find exactly the curvatures about some principal directions. Now, the qualitative picture that we expect from this theory is as follows. You have different scenarios according to the phase where you are. If you are in the overparameterized phase, so in the blue, in the top phase, where you can fit everything, your loss at the end is by definition zero, identically zero, so it means that also the Hessian is zero and the spectrum is concentrated only in zero. Imagine now that you go down, that you move towards the transition. At jamming, you should have a finite fraction of eigenvalues that is zero, a finite fraction of flat directions, and the bulk of strictly positive curvatures. And if you imagine that now you go slightly below the transition in the underparameterized phase, the first difference is that you just blur this peak, this delta peak in zero. And of course, if you move in the bulk of this underparameterized region, you start mixing these eigenvalues. Now, numerically, I'm just going to show you what happens at jamming. And here is
This picture is like a hypothesis.
Well, no, this is the result that you can find. Really, if you impose the stability of your minimum, that is that your minimum cannot have negative curvatures, then you find these conditions.
Then why should the loss be identically zero? I can understand that.
The what, sorry?
Why should the loss be identically zero
Yeah.
in the overparameterized regime?
No, well, you suppose that the loss is zero, and this defines what is the overparameterized regime. If you assume that the loss is zero and that you find a stable minimum, this gives you the upper bound that I had before. So if you know that the loss is zero and that you are stable minimum, for sure, I mean, this happens for sure if you're above that one. Okay.
So why do you call it almost flat?
Well, I mean, it's not really almost flat, but you have a finite fraction of flat directions. Yeah, it's not the proper. You have a finite fraction of flat.
Right?
Yes, yes.
50% of the.
Yeah, but it is a finite fraction. It's not just two. It's a finite fraction of flat directions. So numerically, I am just showing you what happens at jamming. Now, these are three different curves for three different depths, almost the depth. Now you see that there is a huge concentration of eigenvalues in zero and some positive bulk. Now I have to comment a little bit. Here there is some blurring of this delta, and there are several reasons for this. One is that finding jamming already in granular matter is very difficult computationally. For networks, it's even tougher because you really have some jumps that you can make in the number of parameters, and it is difficult to initialize the simulation to get close to jamming. So what we do here is just stimulate a lot of networks and pick those that are close enough.
I'm surprised by one thing here.
Yeah.
is just out of the blue. I would have expected, when you have the transition in Wishart matrices,
Okay. Yep.
and as in the simple GLM I was describing simpler than that, there was this Wishart matrices hidden behind the complexity. Yep. The transition is you go from a Dirac mass to at some point you have this shift, but the transition is touches.
Yes, at some point, yes.
You have a Dirac finite fraction at zero.
Here it is not. No, actually, this is the difference between the jamming of spheres and jamming of ellipses. In jamming of spheres, what happens is very similar. Here it is the same. Sorry, no. The difference for jamming of spheres is that instead of having this gap, you have a power law. You have a soft gap, okay, a pseudo gap. For ellipses, you really have a hard gap at jamming and also slightly below jamming.
So there is really a gap.
Yes, I mean, this is true.
So when the other eigenvalues appear, so you start from flat, everybody's zero.
And then you have something finite.
And then when they appear further away.
Probably, I mean, what is continuously growing is the mass of this bulk. Yeah, but so I was saying that it is difficult to find points exactly at jamming for deep networks. So here we are mixing some points also in the other two phases. And also since some points are coming from the underparameterized phase, we stop the dynamics at some point.
I'm learning jamming.
Yeah.
So it means that at the jamming transition for real jamming, not this,
or spheres.
You have low modes.
You mean for ellipses? For ellipses.
No, for spheres.
For spheres, yes. For spheres, here you have really a pseudo gap. You have a distribution that has a power law going to zero.
You're saying this is for
This is for ellipses. Yeah.
So for ellipses you don't have
no.
Because there's some
exactly. For ellipses, you have
the disorder.
Yeah. For ellipsoids you have a gap, and for spheres you have a continuous.
This is proof for jamming?
Yes, for ellipses, yes. At least I think that the proof is based on ellipses with a small eccentricity. Yeah. So it's asymptotic in this, but I think it should be proven. Yeah. Okay, so this speaking a little bit up. So this result there is a good agreement between the prediction and the result. So the first answer is yes, we can fit all the training set if your network is sufficiently overparameterized. This is kind of an expected result. Now we are moving on to the second part. So we're going to see what happens to the generalization error if you change the system size. Now, it seems for what concerns training that you just want to crank up the size of the network. But if you do this and you look at generalization, you should worry about overfitting. Let me tell you what overfitting is. Let's think about a classical example, that of polynomial fitting, polynomial regression. You want to do some mean square regression with a polynomial of degree n. This means that you have n parameters. Imagine that you want to fit these points. They look like they follow a parabola plus some noise. If you try to fit them with a line, of course, you don't have enough complexity to model your data. If you use a parabola, this seems to be the best thing that you can do because there is some irreducible error. And if you increase the degree of the polynomial, at some point you start fitting the noise. In particular, if the degree of the polynomial is equal to the number of the points, then there exists a polynomial that passes through all the points. So you can achieve zero training error, but you know that this is not describing your data at all. The generalization will be awful. And indeed, we can see this in a plot. Here I'm plotting the x-axis is the degree of the polynomial versus train and test error. The blue line is the train error. You see that it decreases monotonically, and it gets to zero when the degree is larger than the number of the points. But if you look at the test error, it reaches a minimum at the previous value, and after that, you just increase your error monotonically. This is a classical picture in inference. So what happens for networks? We expect something similar. Of course, we can measure what happens. So what I'm going to do is, this is the same phase diagram as before. If you fix the size of this dataset, you can train networks of increasing size, passing from the underparameterized phase to the parameterized phase through the transition. And this is what we observe. So, of course, I can do this for different sizes, and I'm going to plot 3 curves, one for each size of this dataset. And here, as you can see, this is nothing like what happens for classical statistics. Here you don't have overfitting in the sense that asymptotically, when n is large enough, when the network is large enough, your test error monotonically decreases. If you increase your size, you cannot do worse. There is just a catch that at intermediary values, there is a little portion where you do overfit. In this part, when you increase the size of the network, you do also increase the test error, and you have a cusp. What is very interesting is that if you scale the axis by the size of the network at jamming for a specific P, the cusps collapse. So this is also very reminiscent of a phase transition. This is exactly the point where you manage to fit all your training set. At this point is where you overfit the most, but beyond this point, your test error monotonically decreases. Now this has been, it's kind of ubiquitous nowadays. It's been observed in many different architectures in deep learning. It has been observed first by Advani and Sachs. Then we observed it with these plots. Then Belkin gave it the name of double descent. This is how everybody calls it nowadays.
So N is the number of data points.
No, N is the number of parameters, the network size.
So you mean to say with the more number of parameter size, your test error actually
Yes,
decreases?
yes. The more you have, the better it is.
So that is counterintuitive to the overfitting.
Yes, exactly. You don't have overfitting here. I mean, you have overfitting at intermediary values, but beyond that point, you don't overfit. Your network kind of...
Infinite amount of data.
Sorry?
Do you assume finite amount of data?
Yeah, P is finite, so you fix your dataset and then you change only M. This is what you do.
Oh.
But still, if you do classical fitting with this, with a fixed size, you don't have this picture. You have what I showed you before. If you fix the size of your dataset P and you do polynomial fitting, let's say you find something like this.
Right.
So the difference is that in some sense, these networks are kind of self-regularizing. They have some automatic regularization.
Is this generalization or the test error?
This is a test error, the generalization error. I mean, it's the expectation error computed with a finite test set.
What is the non-linearity that you're using?
Here we're using, I think here it was ReLU, but we did also experiments with soft plus, and also with a hyperbolic tangent.
It's the same behavior?
More or less, yes. I don't remember exactly, but yes. I think for the hyperbolic tangent, I didn't look at these curves, but the jamming part was the same, yes. Actually, I didn't show the plots, but we studied jamming both with TAN-H and ReLU. In both, we have critical exponents. They are different, they are not universal, but you have the same overall picture.
So this is ReLU, gradient descent.
Yeah, full batch correlation. This, I don't remember if it was for 3 or 5 layers, but all the previous data. No, there's nothing else. Yes, exactly. And still it is kind of automatically regularized. What?
Do you also see the same for SGD?
Yes, we do. Actually, Mari is going to show something. You do SGD also in some of your results? In some of the plots that you're going to show, you do SGD? Okay, no, it's only GD, only gradient descent.
The other question, N, so is it, it's H squared L, right?
Yes, I mean, there is also biases, but yeah, that's it.
No, but is it, does it depend on whether it's more thinner or wider?
Well, it seems no, at least, I mean, in these plots, we are fixing L, so we don't cross-validate across different L's, so I cannot really answer to this question.
N is N squared, you've got...
N is H squared times L.
H squared.
Yeah, yes, exactly, yes.
I'm just trying to understand if it's, this phenomena is more prominent if you have more layers or if it's wider.
Yeah, I cannot really, I don't have an answer for that. Okay, so the point is that now we have some heuristic argument to justify why we have this monotonic decrease in the test error. And
but there's also a recent proof of double descent in several cases.
a proof? Well,
Yeah, Sonnet and Montanari.
Well, but that is only one hidden layer.
Yeah,
I mean, it's a different, but I mean, there are two differences. One is that it is one hidden layer, and it is in a specific region that is the mean field limit regime. In principle, for networks, you have two different limits, and Mario is going to talk about this. Okay, so sorry, I was telling you that we have some heuristic description of this behavior, and this monotonic decrease is actually due to fluctuations. Why fluctuations? So your output function that you learn is actually a stochastic quantity. And this is because the initialization is random. So whenever you initialize with a different initialization, you find a different set of parameters. In order to quantify these fluctuations, we can look at averages and variances. So the first trivial average that we can define is what is called the ensemble average. So imagine that you train n copies of your network with different initializations. You find different parameters W. And if you present a novel input, a test input to these functions, they will tell you, they will give you different predictions, typically. So the ensemble average is the average of the predictions of these different functions. It is the easiest way to remove some kind of fluctuations. Then you can compute the variance by considering a norm of the difference between a single instance and this ensemble average. Now we plot this quantity with different norms. We use a sum over all the test points, train points, all random points. In the end, it has the same scaling with the network size, in the case as a power law, with this exponent. And in the end of my talk, I'm going to tell you why there is this scaling. For the moment, just have faith in me.
So the ensemble here, the randomness you're talking about is not the randomness of the data.
It is random. No, also because here there is no randomness in the data because we do full batch gradient descent. So the data is just given. It's not.
It's completely quenched.
Exactly. Yes.
The randomness
of the initialization. Yes. Yeah. Indeed. Yeah. Of course, if you do stochastic gradient descent, you also have another source of fluctuations. Okay. So for now, let's take this for granted. I'm going to justify this later and see what are the consequences for the error. So just a minor remark, it is clear that the test error of this ensemble average of the outputs it is not the average of the test errors of different networks. And you can see this very simply by plotting these two quantities. So here, each blue dot is the test error of a network of a given size trained independently. You see that the solid line is just the average over different instances. And this is more or less the curve that I showed you before. You have a peak and then a monotonic decrease of the test error. And the orange line is the test error of this ensemble average. And there are some remarkable results. First of all, beyond jamming, this test error seems to be almost flat. This is something that we don't understand. We don't have a proof for this. But in many cases, it looks almost flat right after jamming. Second point is that since when we do ensemble average, we are killing these kind of fluctuations, it means that all this error, that is really a lot, is induced by these fluctuations. Is induced by these fluctuations. I mean, if you remove the fluctuations, you remove this error. And also, with just a purely heuristical result, it seems that the best thing to do in order to achieve the best performance is to train a network right after jamming, let's say at a network that is 3 times larger, and do ensemble average. This is really the point where you achieve the best performance, and it does not only happen here, that is just a fully connected network on MNIST, but it also happens if you use convolutional neural networks on the CIFAR-10 dataset that is much more complex. Here you have the same plot, you have jamming, you have this CASP, and ensemble average is also the best right after jamming.
How many points do you take to do your ensemble average?
20, I think.
So it's not...
Or less than 20.
It's not something...
The convergence with N is very fast. It's something like random. It's really random point.
You're taking 20 different initializations,
yes.
And then you take the average of...
Yes, exactly.
That little
yes.
thing, and that's enough?
Yeah, and imagine, if you look computationally, instead of doing 20 networks, if you move to a network that's 20 size larger, you don't have the same performance. And even if you add the memory-wise, it would still be convenient to do that in parallel. But yeah. Okay, so you see, fluctuations are giving you this error. So we are going to describe why these fluctuations decay with the size. But I mean, what is missing is still to understand why this ensemble average is flat. This is something that for me is still unclear.
This is the average of the waves?
Sorry?
This is the average of the outputs?
Yeah, so you take the average of the outputs and then you use this as a predictor and you compute the test error of this prediction. So each network tells you this is a dog, this is a cat, this is a dog, you do the average and you use this as a prediction. You do a majority rule.
So you average the logics?
No, yes, exactly, yes. Yeah.
So you multiply the problems?
I should think about it.
So if one of the network wins, boom, it goes down.
No, but you really average the prediction. So if a network has some prediction, whatever is the value of f, the output, you take its sign and you do average of the signs. So you have a network that really, once you take the sign of the output of a function, you have network that tells you +1, -1, +1, -1, and you do the average of this number, and you use this as a prediction. So there is not a network that can win by having a larger weight, if this is what you mean.
So this should be well known because ensemble methods only do that, like tagging, right? You train many models.
Yeah, but I mean, it is known in the law that doing averages works. I mean, the Netflix prize has been won by someone that mixed hundreds of different models. So mixing and averaging is a way to kill fluctuations. That is known since a long time. This is for sure. It's not a novel idea. I mean, the idea of doing ensemble average is done in practice to reduce errors. This is known. Okay. Yeah. Here, just saying that this is also the reason why, I mean, you can link the decay of these fluctuations to the decay of this error.
But it's surprising that you just need 20 points.
It's remarkable.
This
Yeah.
is
Yeah.
bizarre.
Yeah.
Something-
You're really able to kill a lot of this noise.
Is there any analogy to that in the jamming situation?
Not that I know of, no. At least I didn't think a lot about it, so, but I don't see a clear analogy. Okay, so let me just skim quickly to the rest of the talk. We have a very basic scaling argument. This is not formal proof, but imagine that each function is actually a boundary interface in the input space because it separates point where it assigns a positive label to those where it assigns a negative label. And this is a fluctuating random boundary that fluctuates around this ensemble average boundary. Now, if you assume that the test error, not the train error, is a smooth function of this boundary, and that by symmetry considerations, the first term that can appear in an expansion has to be the quadratic term, very trivially you find that this distance, this gap, has to scale as the fluctuations, as the variance of this function. And we can check this numerically. So the problem here is that there is a slow convergence. The blue line is the numerical gap. This triangle is the predicted power law. In order to find the dotted line that seems to match reasonably well the data, you have also to consider the higher order terms. So this data is not the cleanest one, but there is some reasonable agreement with this simple prediction. And if we trust this result, the only thing that is missing is to justify this scaling of the variance. And to do this, we have to understand how a function behaves in the infinitely wide limit. Because I mean, here we're talking about large n, and for us, the depth is fixed, so we just have to increase the width. If you take a network, well, let me skip this slide. This is a result that has already been introduced by Lenaik yesterday. It's a result by Jaco and collaborators. In general, let's say that you take a small h, a small network. If you look at the gradients during training, there are some evolving quantities. These gradients evolve during training. This means that your function with respect to parameter space is living on a curved manifold. When you take the infinite width limit, these gradients become constant. It means that your function lives on a flat tangent manifold. Or you can see this in another way by saying that it stays close to its initialization, in the sense that the total distance traveled by your parameters during training scales the case with the width of your network. Now, a more exact formulation of this is that you can write the evolution of the output of your function. This is an exact formula. Don't pay attention to the details. It's just here to tell you that the evolution of this output is some sort of function of this function of two variables. This is a kernel. And it also has a simple expression because it is a scalar product of the gradients of your function. Now, in general, for small networks, this formula is useless because this kernel depends on time, because the gradients are evolving, and it is also random because of the initialization. The remarkable result by Jaco and collaborators is that, just informally, in this infinite width limit, this kernel becomes constant along training and deterministic. It does no longer depend on the initialization, and you can actually compute this exactly, at least for this fully connected architecture. So, I mean, this has many consequences, but the fact that this function is constant and deterministic means that this is some sort of linear model called kernel methods, and it's pretty simple to analyze. And our goal is to compute the fluctuations of this quantity at the end of training. So you see that if you understand the fluctuations of this quantity at large system size and how it evolves with time, then we can deduce these fluctuations. So the evolution in time of this kernel, has been found by Jaco, and it has some scaling with the system size. So the total evolution in time of this kernel is pretty small. In the case, it has n to the power -1/2. And we had some heuristic scaling to show that the fluctuations at initialization are much larger. The decay is n to the power minus 1/4. And this has also been derived more formally recently in these two papers. So if you just integrate over time the evolution of your output, you see that the fluctuations of these objects will be dominated by fluctuations of the kernel at initialization. And this is what gives us the scaling that I told you before for the variances. So I think I'm quitting here because of time, but this is my conclusion. So we said that we can fit everything if we are sufficiently overparameterized. And we don't overfit, and this is really surprising because in classical statistics, you'd overfit and you would expect to be the same also here. So this implies that there must be some hidden regularization in these networks. If you want to check some kind of dual question, how the test error scales with P, we also have a paper on this, but it is not exactly on networks. It is a work where we find the test error of the kernel teacher-student problem, and we find novel exponents. And this is relevant to this point because in some particular limits, these deep networks tend to kernel methods. Thank you.